capacitor, which pulls the output down to ground. So actually what you end up with, I'll just draw it as a straight line, but at low frequency, all of the amplitude comes out, and at high frequency, it sort of tends almost to nothing at all. So you've got something roughly that's looking like that, yeah? Capacitors conduct under high frequency, and they're open circuit at low frequency, right? So, I don't think it's, so that's a low pass. So I don't think it's a great leap of faith that if I show you this, that this is a high pass. So looking at it, what happens if I put in high frequency here? This conducts down to ground a little bit, but it's fixed because it's a fixed resistor. So what happens, the high frequency will come through here, but the low frequency is blocked. So I have quite the opposite kind of effect. I end up with something that looks like this, assuming this is frequency and this is amplitude. Maybe something that looks quite the opposite. Yeah. Yeah. So what I want you to do in multisim is I want you to put this circuit in, go into the analyses and simulation, and plot the opposite graph, which is going to look like that, just to remind yourself of what you were doing yesterday. Okay? So it should be the same in reverse. And once you've done that, I'll show you some maths on this so you can derive the Laplace transform domain version of this, so you can see that mathematically what we see here is also true. Okay, so we just do, and that's based on potential dividers, of course, because if we don't have reactive components, remember the first circuit we did was just this, wasn't it? And that, we have V in, we have V out. So all of these filters are based simply on the potential divider principle, which is just this R2 upon R1 plus R2 times V in equals V out. That's it. And that's really where all of this has come from. Okay? So model it, verify it for yourself. Okay? And then I'll show you some quite interesting maths a bit later for that. Okay?